This is an introduction to Module 4, which is going to cover Chapter 3, in the sections 3.1 and 3.2. In Section 3.1, we're going to be looking at some linear models. So this is where we begin to see how the differential equations that we've already become familiar with can help us understand real-life problems. And so in 3.1, we're going to do those. We're going to use linear equations and look at linear models. In particular, we'll look at two kinds of problems: population growth and the law of cooling and warming. And then in section 3.2, we'll look at a nonlinear equation, the logistic equation that allows us to understand also population growth. So section 3.1, population growth, the statement that the model that we're going to create is going to be based on the fact that the rate of growth of a population is proportional to the population present at time t. So the rate of growth, that speaks to us about a derivative, and then is proportional, tells us that there must be a constant of proportionality, like this k right here, proportional to the population present at time t. So that's what this p here is going to stand for. So from this assumption or this statement that the rate of growth of a population is proportional to the population present at time t, we come up with this differential equation. And then that's a differential equation that we can solve by the methods in sections either 2.2 or 2.3. And we can come up with a solution being p of t equals p0 e to the kt. And that's for some initial population p0. So p0 stands for an initial population. The second kind of problem that we will look at in this section 3.1 has to do with temperature. And here we use the law of cooling and warming, which says that the rate at which the temperature of a body changes is proportional to the difference between the temperature of the body and the temperature of the surrounding medium. So again, the rate at which the temperature of a body changes, that speaks to us about a derivative, is proportional. Then I know there's going to be a constant of proportionality, and then that needs to be multiplied times the difference between the temperature of the body and the temperature of the surrounding medium. And you can see that this is exactly the differential equation that we obtain. And again, it's a differential equation that we recognize and that we're able to solve. I went ahead and posted here, this is something I found on the web, derivation of finding the solution. And by using this method, then we can come up with this the solution to this differential equation. And again, here T0 is the initial temperature. Now finally, we in section 3.2, we looked then at nonlinear models. And here's where we consider the population growth that no longer has just a constant of proportionality. You can think of the fact that if a population grows in a way that where the proportionality is constant, then that cannot deal with any issues that can occur in the environment. So for example, you might have a pond and you only have so much room for the population to grow in. So eventually you have to account for other things like death or the inability of the environment to sustain the population. And so taking care of that, we use a different differential equation where we replace the constant of proportionality from the original equation, and we replace that with a linear function of the population that at least is going to give us a little bit more of a reality in a population. And in fact, this differential equation has been used by various scientists. It's called the logistic equation. So we can solve this differential equation. You can see the derivation in the book, and it would be this. And the nice thing about this differential equation is that it allows for what is called a carrying capacity, meaning that, you see, if I take t as it goes to infinity, this solution here is going to go to a over b. And so that means that my solutions eventually will never pass k, the carrying capacity, and eventually will come close to k, as it does here. So again, this differential equation acknowledges that there's a carrying population or a carrying capacity of the population.